everybody. Welcome to the first lesson on regression. This is the first of 3 that we're going to do. In today's lesson, we're going to introduce the concepts behind linear regression. And then next class, we're going to look at some of the assumptions of linear regression. And then following that, we're going to get into how do you create a model using regression. All right, so to get started, suppose we take a sample and we've got a bunch of paired values x and y, and we want to use the x's to predict the y's in a linear equation. This is what that equation looks like. X is our independent variable, y is our dependent variable. This is a y with a hat on it, and it's actually called y hat. This is what tells us that this is the regression line based on sample data. So this is essentially y equals mx plus b, except it's really b plus mx. But b naught is our y-intercept, b1 is our slope. All right, and again, the y hat means that this is on sample data. But it doesn't have to be just one independent variable. We can have any number of independent variables, and when we do that, we call it b naught plus b1 x1 plus b2 times x2. Our variables are x1, x2 up through xk, and our coefficients are b naught, b1, b2 on up to bk. And we still have the y hat to show that this is built based on sample data. Now, there is a population regression equation, and this is really what we're trying to infer to. So in theory, there's this population regression equation, and this the sample regression equation is our best estimate for that. Okay, so that's what we're trying to come up with this model as closely as we can. So anytime we want to do statistical inference, that means there's going to be a hypothesis test. So we said we're trying to use this model to infer about this model. If we pick this apart one coefficient at a time, and we really don't think about the y-intercept or the intercept, the constant term, because that one we just hardly ever interested in. But otherwise, if we look at each one of these coefficients, if that coefficient in the population were 0, so if, for example, beta 1 were 0, then that means that this term is beta 1, or this term is 0 times x1, which means that this whole term falls out of the model, which means that x1 would not be a good predictor for y. So x1 would not belong in the model. And that's what this hypothesis test is doing. It's determining for each one of these variables, should we keep it in the model? And if we are stuck concluding that beta equals 0, this means that the variable does not belong in the model. So we're going to assume it doesn't. And then we're going to look for evidence that it does. Okay? So we're going to do a hypothesis test for each one of these slope variables here. So now let's look at how to get this in SPSS. So I made up this data set, and I didn't make up a context for it, just x1, x2, up through x6, predicting a y variable called y. So to get the regression equation, we're going to go to Analyze, Regression, Linear, And we're going to put our y variable in the dependent box. And any x variables we want are going to go in our independent box. Okay, so x1 through x6 are our independent variables here. So we're going to put that in the independent box. And then we're going to click OK. All right, so we get this output, which I've already copied over here. And we're going to come back and look at these first two tables in just a minute. But for right now, let's just look at our regression coefficients. So where it says unstandardized coefficients, the B's, this is what we want. Oh, I'm going to turn the draw on. So under unstandardized coefficients, B, those are our regression coefficients. So this means that our regression equation is y hat equals 0.317 plus 1.161 times x1 minus 0.020 times x2 minus 0.743 x3 plus 0.174 x4 plus 0.094 x5 plus 0.012 times x6. All right. So now if we look at these p-values over here under sig, remember we don't care about the one for the constant. We just want the rest of these. So if we use the 0.05 as our cutoff, then only this one is significant. All right. So according to what we have here, x1 is the only one that we would keep in the model. It's going to be a lot more complicated than that. That's what we're going to do in 2 class periods from now. But that's a start. And you don't need to do, write out every time here's H0 and HA, because there's so many of these all at one time. All you need to do is say that this right here, at the 0.05 level, only variable x1 is statistically significant. Now, if we wanted to predict a value of y for certain values of x1 through x6, all you have to do is plug in. So where x1 is 19, just plug that in for x1 and do the math there. So our predicted value of y would be 10.73745. So now let's talk about something called residuals. First, let me clarify that yi are individual values of y. So that's y1, y2, y3. So if we look at our data over here, y1 would be 1, y2 would be 3, y3 would be 3, etc. And y hat I is going to be the predicted value for the first, second, third, etc. Okay. So if I were to plug in x1 equals 1, x2 equals 1, x3 equals 0.7, x4 equals 0.1, x5 equals 1, and x6 equals 2.5 into that regression equation, the result would be y hat 1. Okay. So the residuals are the difference between each individual data point and its predicted value. All right. So I made up this other example so we could see one with just one variable. The hours spent studying for a test versus the grade on the test. And that's what's over here in this SPSS file. For some reason, there we go. Yeah, so I just made that data up so we could see. So if we go make a scatter plot, and I meant to show you how to make a scatter plot earlier. I think I skipped over that. So to make a scatter plot, actually, no, I didn't skip over that. I showed you how to do that last class. So under Graphs, Legacy Dialogues, Scatter Dot, Simple Scatter, the number of hours somebody studied on the test is going to be the independent variable, and their grade on the test is going to be the dependent variable. So we're going to click OK. And that's our graph. It can be nice to see the regression line on that, so let's do that. There's not a way to get it there under options in the dialog box, so we have to double click on this and get this to come up. And then if we click this right here, Add Fit Line, it will put our regression equation on there. Okay. So that's this little box right here where you see the line that looks like it's fitting the data. So I've copied this graph over here, and let's say this is our first point. It's not the first point that's actually listed in the data. It's this point here, but let's call it our first one. So this point here is going to be y1. Okay, that's the value. That's the actual value of the data at x equals 0. Okay, because this is our x value here. That'll change from problem to problem and from point to point. Our predicted value is the y the y on the regression equation that corresponds to the same value of x. All right, so this value here, which my mouse pen is giving me a hard time drawing, but it's the point there that's on that line. This is your y1 hat. All right, the distance there is our residual. Okay, and in this case it's negative because it's always the yi, it's the y1 minus y hat 1. Okay, so the residuals are all of the distances from the regression line. Okay, and we hope that our residuals are small, because the smaller our residuals are, the better the fit that line is. Okay, because that means that our points are tightly clustered on that line. So it's going to come in handy later on to be able to save the residuals. And to do that, when we run our regression, let's say we wanted to do this one with just the one variable. Hours studied is going to be our independent variable. Grade on the test is our dependent variable. And to save the residuals, we're going to click Save, and then Unstandardized Residuals. We can save some other things too, like the predicted values if we wanted to see those. But this is going to come in handy later. And let's watch what happens when we click OK. It's not really going to show us anything much in the output, but if we look back at the data set, it tells us these are our residuals. So for this one, the one we were looking at on the plot, the residual was negative 12.679. Right? So this is going to be important for when we need to do things like check normality of residuals. And we can, once we've got this in here, we can just check normality using the same methods we've been using. So now let's look at some ways we can determine how well the model fits the data. Meaning, is the linear equation that we have using the particular variables and all of the particulars there, is that a good way to predict y? Okay. The first thing we're going to look at is something familiar to us, which is the r squared, which is the coefficient of determination. And that is the same interpretation as we saw with ANOVA. In fact, regression and ANOVA are the same thing. Just the big difference is that your independent variable with regression has a whole lot more possible values because it's a continuous variable rather than with ANOVA it was categorical. So this is the same interpretation as before. This is the proportion of variation in the dependent variable that can be explained by the model. Every time we add another variable, the coefficient of determination is going to increase. All right. So let's look at, let's go back and look at our output and find our coefficient of determination. So this is our r squared. Equals 0.998. This was for the one where we were using x1, x2, up through x6 to predict a value of y. All right, so this was an r squared of 0.998. So if we come down here, we had an r squared of 0.998, which means that 99.8% of the variability in y can be explained by this model. Okay? So that's a very high coefficient of determination. This means we're able to nail down what y is pretty closely. If we were to just use one variable, let's suppose we went back and instead of using all x1 through x6, what would it be if, I'm going to hit pause while I log back in here. All right, so let's suppose that instead of x1 through x6, we just use x1. And I just want to show you what would happen to the coefficient of determination. So here we've got just one variable. Our r squared is 0.982, and that's because we don't have as many variables. Okay, so every time we add another variable, r squared is guaranteed to go up or at least stay exactly the same. Okay, so it'll be greater than or equal to, almost always greater than, what it was with fewer variables. So then the question becomes, why wouldn't we just always add more and more and more variables? Because we like our R-squares to be high. Well, the answer is that there's something called the principle of parsimony, which means that we don't want to overfit the model. We want to include enough variables to fit the data, to fit our y value of data, y value in the data. But we want to use the fewest number of variables that we can to do that effectively. Okay? It's like what your doctor does when they're prescribing you medicine. They want to give you enough, but they really don't want to give you any more than that. So if we overfit the model, then it doesn't really generalize as well. So we want to keep it down to a reasonable number of variables. All things being equal, fewer is better. So all that is to say, we've got something else that we can look at called the adjusted R-squared, which is the same as the R-squared, but it's adjusted for the number of variables in the model, so that you can directly compare and determine whether it's worth it to include these extra variables. Now, be careful with the adjusted R-squared because you cannot use this variance accounted for interpretation with it. This is strictly for the sake of comparison. So here, our adjusted R-squared is 0.995. And if we were to compare 0.995 to the adjusted R-squared that we get over here, 0.979, we'd have to consider whether it was worth adding those extra variables. So that's the first part of assessing model fit. The second thing we can do is an F-test. And before we looked at individual variables for whether they belong in the model, this test is an overall test to say whether any of the variables belong in the model. So is there at least one variable in the model that belongs there? Okay, the individual tests can't look at them all simultaneously, and that's what this one does. So this value, this test statistic and p-value comes out with our variables up here. So this is in the ANOVA table. And this actually is the same F-test and p-value we saw with ANOVA. So our F-test statistic is 293.625, and our p-value is less than 0.001. So this tells us that that we can conclude that there should be at least one variable in the model. Okay, if there shouldn't, then this is called the intercept-only model. Which would mean that all of the predicted y values would just be the mean of the y's. For this value, for this model, the model that we were using x1, x2, up through x6 to predict y, our model had an F value of 293.625 and a P less than 0.001, which means that this model is statistically significant. Okay, so this points to a good model. So that's it for this lesson. I just wanted to leave you with a summary of some of the notation because I know there was a lot of it. We've got our population regression equation. These are the y values and then the individual y values. The first one is the y value from the equation. And then the same thing for our sample regression equation. The y value from that equation and then the individual predicted y's. We've got our slopes and our y-intercept for the regression equation in the population and the sample. E for error, these are our residual values. And then we've got our r squared, the coefficient of determination. All right, so that's it for this lesson. And, as always, if you have any questions, please let me know.